Welcome to the course on Introduction to Electrical Engineering. We will discuss today in lecture 11 the single phase AC circuit part 1. To start with outline of today's presentation, we will start of course introduce the topic, following with the single phase appliances where we use the single phase supply. Then we will talk about the basics of sinusoid and phasors. Then we will talk about average root mean square value of an AC quantities, and followed by steady state AC resonance for a pure resistive circuit. Then we will talk about exercise and numerical analysis like. So, to start with, why alternating current power system has become popular. When direct current electricity flows into one direction through a wire, AC electricity alternates its direction back and forward, that is shown here. Well, AC electricity is created by an AC electric generator which determines its frequency, and the major advantage of AC electricity is that the voltage can be readily changed with the help of transformer, thus making it more suitable for long transmission system than DC electricity. Apart from that, it allows to operate this transformer action, which we can change the voltage easily or readily allow the generation at optimum voltage, transmission at optimum voltage, then distribution at optimum voltage, as well as utilization of this AC power at optimum voltage. The another major benefit of this AC supply system is that the cost of switching is also reduced, because this current passes around like typically 100 times to 0 value because of alternating nature. So, the cost of switching, or you can call it switch of AC switches, are much, you can call it a smaller size, cost effective, as well as the contact is also not very severe. I mean, because of this, that is also another major reason, I mean, why we have to go for typically of, and moreover, I mean, the AC generator as well as motors are much economical than the your DC motor and DC generators like. So, these are the reason why we adopted the AC, some of the reason why we adopted AC supply system. I mean, like, of course, you can say AC supply can be applied by using capacitors and inductor in electronic circuitry and showing a wide range of application, and the representation of AB wave can be of various kind of waveform. It is shown like sine wave, or you can call it like typically a complex waveform, or triangular or square wave. The question is why we adopted sine wave. I mean, we already discussed that you can change the voltage from one level to another level from transformer action, and the transformer action can be perfectly or with minimum losses, I mean, can be done only with the sine wave. If you take other wave, because through transformer action, if you look into the phenomena according to typically a Faraday law of induction, that you have to go through derivative as well as you have to go through integration. So, if you talk about like a kind of derivative or integration for other three waveform, then sinusoidal, certainly the waveform get distorted, and you will not get the same typical RMS voltage as well as the current flowing through the you can call it through the transformer. But sine wave certainly also get converted only into the cosine or sine get. So, the waveform is not changed, only the phase shift is there in case of sine wave, and that is because the other presence of other harmonics which are in other three waveform, they increase the losses in the equipment typically either in generator or maybe transformer as well as in the your motors and other equipment also, and that is the reason we selected typically the sine wave, I mean, of AC supply system like. Well, you can see how it look like. I mean, the alternating current, like you might be having the changes with respect to the time, all the time depends on the frequency of AC supply and how it really, I mean, have a induction phenomena from one coil to the typically another coil in this transformer action like. And of course, not only the transformer, we have even a wireless kind of induction principle is possible in case of the alternating current, which is not true or possible in case of the DC supply system like. So, well, now we have a lot of even possibility that we have a single phase appliances. I mean, you might have a like very forthcoming generation nowadays with the renewable is coming from the solar, which are normally maybe on rooftop. So, this DC supply we have to convert certainly to the transformer, and then we have to distribute either home and or put to the grid like. I mean, so, but why we are going to be solar, you can think about it. Say now it has become one of the cheapest electricity among all the electricity generating system, either whether you have a thermal power station or nuclear power station or you have a hydropower station. So, I mean this is one of the cheapest, including even lesser than the wind power generation. At the moment in India we have it, I mean only around ₹2 per unit, which is going to be further going to be, we are expecting that next 5 years it will reduce to probably ₹1 per unit or kilowatt hours like or so. So, that is the reason, I mean we are going to the solar, and it is available all the places like, I mean, and means it is a renewable that okay, it is available easily in nature. So, you can probably it is a cost or inexhaustible, I mean till we expect till the nature is there, the solar sun will remain there and you will have a solar energy exposure, and you can run, I mean once you convert this DC of the solar, I mean with the help of inverter and other converters you can store into the some energy in the battery, so that your appliances can be run for 24/7, because the solar is not available all the time like or so. So, but of course, we have in India around 27% already with renewable, which consists of course solar, wind and small hydro as well as fuel cell. So, the time has come like the cost of electricity have to go down, so that I mean really it provides the better facility for the humankind also. Well, you have other single phase appliances, typically like a single phase induction motor, which are huge, starting from typically a very fractional kilowatt rating to some kilowatt rating. I mean like as you can see, maybe having a different kind of starting methods. So, most of the applications which you find a small power rating, I mean in fractional kilowatt, most of the motors are of single phase, whether it is you just take the compressor motor or whether you take typically even a fan motor, or you have like a other appliances or pump small pump application, I mean which are the even less than like typically of 1 kilowatt or so, we call it fractional kilowatt. Most of them are the single phase induction motor. Of course, as we discuss it, we have a different kind of transformer in single phase also. You might have a like auto transformer, which is used only for change of the voltage level without isolation, but the cost is reduced because you, I mean you are not having 2 winding, you have only one set of winding. But of course, we have the transformer which used for several purpose. One of the purpose is providing the isolation or the large voltage level difference. Another is that you can have even a multiple output also. I mean with the help of transformer you can have a single source to connect it to one winding, and then you can have several secondary which can provide the power to different isolated load also. In many situations we require such, I mean conditions even for single phase transformers, I mean like also. Well, we have a single phase welding machine. There is also revolution in single phase welding machine also. We connect from single phase supply, and there have been a typically, I mean single phase supply get of low frequency like 50 hertz or 60 hertz converted into your typically into DC, and that DC converted to high frequency order of typically around order of 100 kilohertz, which reduces the size of the transformer, I mean like in case of this welding machine. And then from the secondary you are able to convert into DC, because DC is more comfortable for the welding. So, that reduces the size of the welding machine. I mean for 5 kVA, I mean the reduction of the size can be typically from probably around 100 kg to hardly 4-5 kg this welding machine also. So, then you have a like a inverter, I mean we have a single phase variable frequency inverters, I mean used for many applications, like I mean maybe like a domestic application, or you may have a variable frequency for motor control. For the purpose you might have a single phase supply, but these appliances are run, I mean the motor may be 3 phase, because you can convert from single phase supply into DC, and from DC you can convert your 3 phase supply of variable frequency, so that it is comfortable. I mean it give a really right foot to your AC motors, matter it can run 3 phase AC motor, which are much more efficient as well as cost effective and have a higher efficiency also. Then you have a typically like your single phase starter for these motors, and then you have a like a single phase meters. Normally most of the, you will find most of the distribution for the home, I mean like supply is single phase, I mean because your most of the equipment in the home is hardly not more than 5 to 6 kilowatt. So, most of the load is 3 to 5 kilowatt. So, there we use only single phase supply. So, you have a single phase energy meter, and these energy meter by which you really measure the energy consumption. I mean they, of course, earlier it has been like mechanical, then it gone to like a typical electrical, and followed by now typically digital like and they have a various features. The digital instrument may be like a smart meter, that in order to go to the premises you can take all the readings sitting remotely or from the network. So, that concept has gone now. All these single phase energy meter also, which we call it with the smart grid and with the proper network connected all meters. So, that really avoids a lot of problems associated with the use of electricity like Then you have a single phase voltage stabilizer. This has been much in use in India, the reason being that in many locations you may not have a very well located, very well you can call it the regulated power supply in far flung area. So, certainly there most of the appliances are designed for a particular voltage. So, it means you have to regulate the voltage so that it feeds the regulated voltage for the equipment, so that your all the equipment, I mean they need not to rate, or they may not be their operation is quite satisfactory and efficient, and they serve the purpose rightly for the cause they have been used for. Like then you have like a typically single phase AC surge protection device, so that all the surges or they are not affecting your load or so. Then of course, we already talk about like a single phase induction motor which used in ceiling fan, and you can find out the typically in India itself around 3 crore fans are manufactured every year. So, you can think about like what the quantity are there for these fans, and well in tropical region, like typically which like India is normally spread over, we use large number of fan in every house or every premises, whether it is commercial building or whether it is your academic building or it is a residential building. You use the lot of fans like with proper speed control, so that you can control the your you can call it airflow, for best comfortable for under changing the weather condition starting from typically from March to typically up to end of October. That is at least in Delhi, but many other part of the country, in India you will find that typically the changing season may require the wide speed control of this fan. Well, then you have a typically single phase refrigerator in your home, which runs with the single phase supply, and it has a typically the compressor inside of it, so that your all food stuffs as well as many other part of your daily use or consumable items are well, you can call it preserved in this refrigerator like. Or you have a single phase television, which you use, or you have a like a food mixer, like these are all operated from single phase supply. Then single phase water pump of different variety, either whether it is a typically booster pump or it is a pump for typically for many other services, or you have a single phase smart energy meter or single phase frequency converter, then single phase protection relay and single phase servo stabilizer, then single phase energy meter, single phase heat pump, or a single phase power supply with battery, or single phase grid connected system of the either typically you can see either from AC generator or typically your solar through the battery, because sometimes grid may not be available in some of the locations, but you have to provide the uninterruptible power for most of the applications and some critical applications. Those critical applications you can think about typically either banking system or your irrigation system. So, plenty of places we require uninterrupted supply. So, it can't afford typically your interruption of the supply system like. Well, the benefit of course in case of AC supply system that you have a even you can make a phase shift required for different purpose, and here you can see that using RC network you can have a phase shift according to the you can design the RC component that input to output you can have a phase shift, like typically here it is a 60 degree. If you have a 3 stage, it can be completely 180 degree out phase shift can be created, or you can create the phase shift with the help of simple network required for some of the applications, as a signals or otherwise like. Well, you have a AC bridges which are used for many purpose for instrumentation or measurement like a resistance or inductances. So, there are a lot of bridge which operate with the single phase AC supply. So, we comes now with the basics of sinusoid. We already discussed why we need, of course, we have a sinusoidal supply this typically in AC system. So, a sinusoid is a signal that has the form of sine wave or cosine function, and sinusoidal current is usually referred as an alternating current, and such a current reverses at regular time interval and has alternately positive and negative value as shown here with respect to time, how it is the current is changing with respect to time as a sinusoidal fashion or manner like. Well, a sinusoidal signal is easy to generate and transmit, and it is the dominant form of signal in the communication as well as electric power industry. Through Fourier analysis, any periodic wave form or signal can be represented by sum of sinusoid, and circuit driven by sinusoid current or voltage sources are called AC circuit, and you can typically have a experience of sinusoidal waveform here of how like a motion of pendulation provide like typically the amplitude is changing either with the frequency, or you can have a second harmonics with the 2f or third harmonic with the 3f, like how we represent the harmonics as a function of typically a fundamental frequency, like just as a practical experience to feel that what is really the sinusoidal or so. Or you can have a ripple typically in ocean wave, that give you the idea that okay, how this in ocean wave you have a like a AC over the DC, typically, and how it is coming in the this signal with proper kind of like offset, or only the AC component you can take out from the these signals like. So, we can say like typically the term which we mostly use is the cyclic and periodic. So, you might have like a one cycle of different periodic function with the different phase shift, but of course, one cycle means even form where you take a starting of the waveform, it had to go to the same value after a cycle, and that we call it for complete cycle. It may be starting from 0 period of sine wave, or it may be with some degree of sine wave. So, that some value is there, or you can have even 90 degree phase shifted also, but you have to cover completely whole cycle of this. So, the waveform, the variation of quantity such as voltage or current shown in on a graph to a base of time or rotation is called waveform, and the cycle, each repetition of the variable quantity recurring at equal intervals is termed as a cycle, and the period, the duration of one cycle is termed its period. Well, the incidence value, the magnitude of waveform at any instant time, and they are denoted by lowercase symbols such as E, V, I, and peak value. The maximum incidence value measured from 0 value is known as peak value, as it is shown in the two figures. And well, peak to peak value, the maximum variation between the maximum positive incidence value to the maximum negative incidence value, we call it the peak to peak value, as you can show in the figure. And the effect of waveform on varying frequency, how it look like. So, you might have a waveform typically of 1 kilohertz with millisecond, or you might have a 2 cycles. So, it will be like a period of 0.5 millisecond. So, it is corresponding to 2 kilohertz, or it may be 0.4, maybe the 0.4 millisecond may be the 1 cycle. So, you have a frequency of 2.5 kilohertz. So, the coming to like a peak amplitude, the maximum incidence value measured from the mean value of waveform is the peak amplitude, and the frequency, the number of cycles that occur in 1 second is termed as the frequency of quantity, and frequency is measured normally in hertz. Of course, earlier we were calling it cycle per second. Now, typically the sinusoid play important role in the analysis of periodic signals, and the derivative and integral of sinusoid are themselves sinusoid, and for these reasons the sinusoid is an extremely important function in circuit analysis. And consider the sinusoidal voltage like V t equal to V m sin omega t, where V m is the amplitude of sinusoid, omega is the angular frequency in radian per second, omega t is the you can call it argument of the sine wave. So, it is evident that the sinusoid repeats itself t seconds, and thus t second is called the period of the sinusoid, and from the figures we observe that omega t equal to 2 pi, where t equal to 2 pi upon omega, and you can just see typically your figure V m sin omega t as a function of omega t, and V m t as a function of time. So, you can just have as a function of time or as a function of your angle theta in radian per second. So, the fact that V t repeats every t seconds is shown replacing t by t plus t. So, V t plus t will be equal to V m sin omega t plus t, and V m sin omega t plus t by 2, and we can call it V m sin omega t plus 2 pi equal to V m sin omega t, that is equal to V t. Hence, the V t t plus t equal to V t, that is repeating in the same manner. Thus, we have the same value at t plus t as it does at t, as well as V t is said to be periodic, and a periodic function is one that satisfies the f t equal to f t plus n t for all the t and for all integers n. Well, the period t of the periodic function is the time of one complete cycle or the number of seconds per cycle, and the reciprocal of this quantity is the number of cycles per second, known as the cyclic frequency of the sinusoid. Thus, f equal to 1 upon t, and therefore, omega equal to 2 pi f, and where omega is the radians per second, that is radian per second, and f is the hertz. Well, a more general expression for the sinusoid can be written as V t equal to V m sin omega t plus phi, and where omega t plus phi is the argument and phi is the phase angle, and both argument and phase can be in radian or degrees. And as you can see the waveform here, that let us examine the two sinusoidal V1 equal to Vm sin omega t and V2 equal to Vm sin omega t phi. So, there is a phase difference of phi between the two sinusoidal, like also that is of phi. So, the starting point of V2 typically in figure occurs in first in time, and therefore, V2 leads V1 by angle phi and V1 lags by V2 by phi. So, if phi equal to 0, V1 and V2, phi is not equal to 0, then V1 V2 are out of phase, and moreover if phi equal to 0, then V1 V2 are said to be in phase as they reach their minimum and maximum value at the same time. So, a sinusoid can be expressed in either sine or cosine form, and when comparing two sinusoids it is convenient to express both as either sine or cosine with positive amplitude such as sin A plus minus b equal to sin A cos b plus minus cos A sin b, and similarly cos A plus minus a b equal to cos A cos b plus minus sin A sin b. So, with each quantity it is easy to show that sin omega t plus minus 180 degree equal to minus sin omega t, and cos omega t plus minus 180 degree equal to minus cos omega t, and sinusoidal omega t plus minus 90 degree equal to plus minus cos omega t, and cos omega t plus minus 90 degree equal to minus plus sin omega t. These relations are very well valid for these AC quantity. So, using these sinusoid can be transformed from sine wave form to cosine form or vice versa for all these mathematical calculations like. So, a graphical approach can also be used to relate or compare sinusoid as alternative to using the trigonometric identity. You can say it is a cos omega t and 90 degree lagging is typically your sin omega t. So, a graphical representation relates cosine and sine wave. So, cos omega t minus 90 degree equal to sin omega t. So, horizontal axis represents the magnitude of cosine, while the vertical axis pointing down denotes the magnitude of sine. And angles are measured positively counterclockwise from the horizontal as usual in polar coordinate, and graphical technique can be used to relate the two sinusoids. And for example, we observe that by subtracting 90 degree from the argument of cos omega t gives the sin omega t, or cos omega t minus 90 equal to sin omega t. Similarly, by adding 180 degree to the argument of sin omega t give minus sin omega t, or sin omega t plus 180 degree give minus sin omega t as shown typically here. That graphical relation is omega t plus 180 degree equal to minus sin omega t. And the graphical technique can also be used to add two sinusoids of the same frequency when one is sine and form and other is in cosine form, and to add A cos omega t and B sin omega t as shown here. Here A is the magnitude of cos omega t and B is the magnitude of sin omega t. So, you just get the resultant of adding these two as a C with the. So, magnitude and argument of the resultant sinusoid in cosine form is readily obtained from, for example, A cos omega t plus B sin omega t equal to C cos omega t minus theta, where C is under root A square plus B square, that is we call it like amplitude, and your theta equal to tan inverse B minus A. So, compared with the trigonometric identity, the graphical approach eliminates the memorization. And now, let us come to the some solved numerical on the sinusoid. Well, the numerical one is the determined frequency in hertz, angular frequency in radian per second, and the amplitude of harmonic voltage sinusoid is shown here, and these are the typically two waveform you can just see here. The solution all four signal in figure have same amplitude of 0.6 volt and the same frequency of 1 kilohertz and the same radian frequency omega equal to 2 pi f, that is 6283.1 radian. Well, coming to numerical 2, determine the frequency, amplitude and phase of the harmonic voltage signal as shown versus the base of cosine, and the solution is the amplitude by inspection is observed Vm equal to 1 volt, and the frequency is determined by observing the entire interval from 0 to 3 millisecond containing 3 full periods, hence t equal to 1 millisecond and f equal to 1 upon t, that is 1 kilohertz, 1000 hertz equal to 1 kilohertz. And for the purpose phase determination, we note that the first maximum occurs later in time than from the base of cosine, which is already peak at t equal to 0. Therefore, the phase must be negative, that is phi is less than 0. So, absolute value of the phase is your phi absolute equal to pi delta t upon t, which gives the phi equal to pi by 3. So, after measuring t and delta t with the scale, so alternatively the same result can be obtained by observing the cosine function equal to 0.5 Vm at t equal to 0. So, phi will be cos inverse minus cos inverse 0.5, that equal to minus pi by 3. Well, coming to numerical 3, find the amplitude of phase, period and frequency of the sinusoid V t equal to 12 cos 50 t plus 10 degree. So, we can call it amplitude is 12 volt, phase phi 10 degree and the angular frequency omega equal to 50 radian per second and t equal to 2 upon omega equal to 2 pi by 50, that is your 0.125 second and the frequency f equal to 1 upon t is equal to 7.958 hertz. So, numerical 4, given the sinusoid 45 cos 5 pi t plus 36 degree, calculate the amplitude, phase, angular frequency and period and frequency. So, now solution is like you have already amplitude of 45 volt and your phase is 36 degree and you have a like a angular frequency of 15.708 and 400 millisecond is the period and 2.5 hertz is the corresponding frequency. Only calculate the phase between V 1 equal to 10 cos omega t plus 50, V 2 equal to 12 sin omega t minus 10. So, state which sinusoid is leading. So, solution as a method 1, in order to compare V 1 V 2 we must express them in the same form. So, if we express in the cosine form, then V 1 will equal to minus 10 cos omega t plus 50 equal to 10 cos omega t plus 50 minus 180 degree and V 1 cos omega t minus 130 or V 1 equal to 10 cos omega t plus 230. Now, you can comparing these two of them, you can just certainly find out typically the angle of the two. So, V 2 equal to 12 sin omega t minus 10 equal to 12 cos omega t minus 10 minus 90 degree and that is V 2 equal to cos omega t minus 100 degree. So, it can be deduced that the phase difference between the V 1 V 2 is 30 degree and V 2 12 cos omega t minus 130 plus 30 or V 2 equal to 12 cos omega t plus 260. Thus, it can be observed V 2 leads by V 1 by 30 degree. So, coming to method 2, alternately we may express V 1 in sine form. So, V 1 equal to minus 10 cos omega t plus 50, that is equal to 10 sin omega t plus 50 minus 90 degree or 10 sin omega t minus 40 degree or 10 sin omega t minus 10 minus 30 degree and from which V 2 is your 12 sin omega t minus 10. So, comparing these two, so that V 1 lags V 2 by 30 degree, this is same as saying that V 2 leads by 30 degree. So, here you can say if you take this way form typically anti-clockwise, you will see V 2 is leading than V 1 in phasor diagram 2. So, method 3 we may regard V 1 as a simply minus 10 omega t with a phase shift of plus 50 degree. Similarly, V 2 is 12 omega t with a phase shift of minus 10 degree. Therefore, as observed V 2 leads by V 1 by 30 degree. Now, coming to the basics of the phasors. So, basic of phasors, a phasor is a complex number that represents the amplitude and phase of a sinusoid. So, phasors provide a simple means of analyzing linear circuit excited by sinusoidal sources and a complex number z can be written in rectangular form as z equal to x plus j y, where j is under root minus 1 and x is the real part of x z and y is the imaginary part of the z. So, the complex number z can also be written in the polar or exponential form. So, coming to polar form, it can be written z equal to r at angle phi or we can write it r e to power minus e to power j phi. So, where r is the magnitude of z and phi is the phase of z and we can say in rectangular form it is z equal to x plus j y and polar form it is same as z equal to r at the angle phi. And you can just have a typically here the diagram representation of this complex number and you have a x real axis, y as a imaginary axis here and you have a typically the z with the you can call it magnitude of r at the angle of phi degree from x axis. So, we can just say the relationship between the rectangular form and polar form is shown in the figure and you can call it where x represents the real part and y represents the imaginary part of the complex number and given x and y we can get r and phi as r equal to under root x square plus y square and phi equal to tan inverse minus x y upon x, where x equal to r cos theta and y equal to r sin phi and z may be written as z equal to x plus j y at the equal to r at angle phi, where r this is equal to r in bracket cos phi plus j sin phi and the idea of phasor representation is based on the Euler's identity. So, e to power plus minus j phi equal to cos phi plus minus j sin phi. Well, by comparing cos phi and sin phi the real and imaginary parts of the j phi, So, we can say cos phi equal to real part of e to power j phi and sin phi equal to imaginary part of e to power j phi. So, where R e and I m stand for real part and imaginary part, and given a sinusoid V t, V m cos omega t plus phi can be written as V t V m cos omega t plus phi as a real part of V m e to power j omega t plus phi, and thus V t equal to real V e to power j omega t, where V equal to V m e to power j phi at the V m at the angle of phi. Well, the plot of V j omega t equal to V m e j omega t plus phi on the complex plane can be observed as here, I mean typically on this form, how it is on a circle it is shown with the time, and how it is shown as a waveform like. So, when it goes to the peak, it means the real part is the peak, when it goes to 0 you are on imaginary axis, and that is really give you the complete concept of this your real and imaginary function like on the real and your imaginary axis. So, representation of V j omega t vector rotating counterclockwise and its projection is on real axis as a function of time. That is the reason we consider this angle as a measure from in the counterclockwise rotation like also. Well, so as the time increases, the V j omega t equal to V m j omega t plus phi rotates on a circle of radius V m at the angular frequency omega in the counterclockwise direction, and phasor V equal to V m at the angle phi and I equal to I m at the angle minus phi are graphically represented. Such the graphical representation of phasor is known as a phasor diagram. As you can see here, imaginary x axis, y axis, and you have a V m at the angle of phi from x axis. This we call it leading waveform or leading waveform, and of course, with the typically at the omega, and with the minus theta, I mean this current from x axis, I mean I m, and you can call it there, that is V, this is I, with the their respective value how we represent it like. So, phasor diagram shows V equal to V m phi and I equal to I m minus theta, and that we call it the representation of course by the phasor. So, by suppressing the time factor, we transform the sinusoid from time domain to the phasor domain, and this transformation summarized as V t equal to V m cos omega t plus phi, and in phasor form we write like V equal to your V m at the angle of phi. And besides the time differentiation and integration, another important use of phasor is found in summing sinusoid of the same frequency, and coming to the some solved numericals on phasors waveform. So, we can say numerical transform these sinusoid to phasor. So, I equal to 6 omega t 6 cos 50 t minus 40 degree, I mean, and V equal to minus 4 sin omega 30 t plus 50 degree, and that is you can call it as a solution I equal to 6 cos 50 t minus 40 degree ampere has a phasor I equal to at 60 at the minus 40 degree ampere, and since minus sin A equal to cos A plus 90. So, we can write V equal to minus sin 30 t plus 50 equal to 4 cos 30 t plus 50 plus 90. So, we can write 4 cos 30 t plus 140 degree. So, phasor of voltage can be represented at V equal to 4 at the angle of here 140 degree. Well, the express second numerical express the sinusoid as a phasor like V equal to minus 14 sin 5 t minus 22 degree volts, I equal to minus 8 cos 60 t plus 15 degree ampere. So, solution is V equal to 14 at the angle of 60 degree volt, and I equal to 8 at the angle of minus 165 ampere, 165 degree ampere like. So, now coming to numerical 3, find the sinusoid corresponding to these phasors. V equal to minus 25 at angle of 40 degree volts, and V I equal to j 12 minus 5 j 5 ampere. So, solution is for A is V t equal to 25 cos omega t minus 140 degree volts or 25 cos omega t plus 220 volt, and B I t equal to 13 cos omega t plus 67.38 degree ampere. So, numerical 4 is give I 1 given I 1 equal to 4 cos omega t plus 30 and I 2 equal to sin omega t minus 20 ampere, find their sum. So, current I 1 is the standard form and its phasor is I at the angle 40 into 40 at the angle of 30 degree ampere, and we need the express I 2 in cosine form. So, the rule for converting to sine to subtract by 90 degree. So, I 2 is cos omega t minus 20 minus 90. So, we can write 5 cos omega t minus 110 and its phasor will be I 2, typically 5 at the angle of 110 degree ampere. Then we can say I equal to I 1 plus I 2, then we can say I equal to I 1 plus I 2. So, that is 4 at the angle of 30 plus 5 at the angle minus 110 degree ampere. So, we can convert it there into this polar coordinate into the rectangular coordinate, which comes 3.464 plus j 2 minus 1.71 minus j 4.698, and that becomes 1.754 minus j 2.698 equal to 3.218 at the angle of minus 56.97 degree ampere. And so, transforming this time domain, we get I t equal to 3.218 cos omega t minus 56.9897 degree ampere. So, now coming to defining like average RMS value of an alternating current. So, let us first consider the wave shown as here, which typical current waveform produced by transformer at no load, and typical you can call it the here heating effect, which is losses into it I square r of it will be average and RMS values of it like So, this is typically the non-sinusoidal waveform which is practically present in the transformer. So, in we can say if n equidistant mid ordinate I 1 I 2 are taken over either the positive or negative half cycle, then average value of current over a half cycle will be I average equal to I 1 plus I 2 plus up to I n divided by n, or alternately the average value of current is area enclosed over half cycle divided by length of base over half cycle. And if I m is the maximum value of a current which varies sinusoidally as, so you can see sinusoid, and the RMS value of this sinusoid caused by heating effect will be I m square, typically I square r, and you can see how it will go to I square r. Typically, it comes to with the average of I square r and I m square is the peak of this like t. So, we can say the instance value I is represented by I equal to I m sin theta, and theta is the angle in radian from instant of 0 current, and for a very small interval d theta radian, the area of the shaded strip is I d theta ampere radian per second, and use of the unit ampere radian avoids converting the scale on a horizontal axis from radian to second like. So, therefore, the total area enclosed by the current wave over a half cycle is equal to 0 to pi I d theta equal to I m 0 theta sin theta d theta, and that is minus I m cos theta 0 to pi, and that becomes minus I m in bracket minus 1 minus 1. So, that becomes 2 I m, and therefore, the average value of the current over a half cycle will be I m equal to I average equal to 2 I m upon pi, that is half period is the pi, and I average equal to 0.637 I m ampere. So, if I is the value of direct current through the resistance to produce the heating effect I square r equal to, that will be equal to half I m square r, and therefore, we can say I equal to I m upon root 2 or equal to 0.707 I m. So, while I edge is the I RMS, it is normal practice to omit the RMS subscript, and this is the most common current like. So, in general average value of the sinusoid current or voltage is I average equal to 0.637 I m, and the RMS value of the sinusoid or current or voltage is I equal to I m upon root 2, that is equal to 0.707 I m, and form factor of sine wave is defined as 0.707 of maximum value divided by 637 minimum value. So, that comes K f equal to your 1.11. So, peak or crest factor of sine wave, we call it form factor, typically crest factor we define it maximum value divided by 0.77 maximum value, that is K p equal to 1.414. This we call it the peak factor, or we call it crest factor of a waveform. For sinusoidal it is root 2, so it is a 1.414 like. Now, coming to solve numerical or average and RMS value of an alternating current. So, coming to numerical 1, an alternating current of sinusoidal waveform has an RMS value of 10 ampere. What is the value peak value of this current over a one cycle? So, I m is equal to I upon typically root 2, that is 0.7 1 by root 2, that is 0.707, that is 10 upon 0. That is 14.14 ampere. So, peak values of therefore is are 14.14 and minus 14.14 for negative side like. Now, coming to numerical 2, alternating voltage has a equation V equal to 141.4 sin 377 t. So, what is the value of RMS voltage frequency and the instantaneous voltage when t equal to 3 seconds. So, the relation is of the form V equal to Vm sin omega t, and by comparison we can say Vm equal to 141.4, that is root 2 V, hence the Vrms will be 141.4 divided by root 2, that comes 100 volt, and also by comparison we can say omega equal to 377 radian per second equal to 2 pi f, f give we are 377 by 2 pi, that comes 60 hertz, and finally V 141.43 sin 377 when t equal to 3 into 10 power minus 3 seconds. So, it comes V equal to 141.4 sin 377 into 3 into 10 power minus 3, that comes 141.4 sin 1.31, and it comes like 141.4 into 0.904, and that comes 127.8 volts, the instantaneous value of the voltage waveform. Now, coming to the numerical 3, a current has the following steady value in ampere equal interval of time changing instantaneously from one value to another as shown in the figure, and the value changes 0, 10, 20, 30, and then comes back again 0, 10, 0, and then comes minus 10, 20, 30, and minus 20, then minus 10, and comes to 0. So, calculate the RMS value of this current waveform and its form factor. These kind of the waveform we have of course in many electrical circuits like of this nature. So, we can take like I average equal to area under the curve and length of the curve. So, we can find out area as 0, pi by 6 omega t minus 0, that is the interval, and similarly we can for 10 into 2 pi upon 6 omega minus pi upon 6 omega, and plus 23 pi by 6 omega minus 2 pi by 6 omega plus 30 4 pi upon 6 omega minus 3 pi upon 6 omega plus 25 pi upon 6 omega minus 4 pi upon 6 omega plus 10 6 omega by 6 pi upon 6 omega minus 5 pi by 6 omega divided by pi by omega minus 0, that comes 15 ampere, and we have now typically I square equal to again 0 square first segment pi upon 6 omega minus 0 plus 10 square in a segment 2 pi upon 6 omega minus pi upon 6 omega plus 20 square minus 3 pi upon 6 omega minus 2 pi upon 6 omega plus 30 square in bracket pi by 6 omega minus 3 pi by 6 omega plus 20 square 5 pi by 6 omega minus 4 pi by 6 omega plus 10 square in bracket 6 pi by 6 omega minus 5 pi by 6 omega divided by pi by omega minus 3. So, it comes 360, and I will be under root of 316, that is 17.18 17.8 ampere, and Kf, that is your typically your form factor I upon I average will be equal to 17.8 divided by 15, that comes 1.19. So, now coming to typically steady state AC response from a pure resistive circuit. So, we have here considered circuit having a resistance ohm R ohm connected across the terminal of AC generator G as shown here in the figure. So, we have a voltage of the generator, we have a current I and across the resistance. Typically if the value of the voltage at any instant B is V volts, then the value of the current in the instant I equal to V upon R, and when voltage is 0, then the current is also 0, hence the sign. Hence, since the current is proportional to the voltage, the waveform of the current is exactly the same as that of the voltage. So, here you can see the two quantity are in phase as they pass through their 0 value at same instant and attain their maximum value at in the given direction at the same instant, hence the current is wave is also shown here. So, voltage and current both are in phase, as you can see the shaded portion is the current and then the per portion is the voltage like in a resistive circuit. So, if Vm Im are the maximum value of the voltage and current respectively, it follows that Im equal to Vm upon R, and both RMS value of sine wave is 0.0707 times the maximum value. So, the RMS value of the voltage V equal to 0.707 Bm and RMS value of current will be I equal to 0.707 Im. Well, substituting the Im and Vm, we have I upon 0.07 equal to Vm V upon 0.707 R equal to I equal to V upon R. Hence, Ohm's law can be applied without any modification to the AC circuit, pausing the resistance only, and if the instantaneous value of applied voltage represented by V small v equal to Vm sin omega t. So, then the instantaneous value of the current in a resistive circuit I will be Vm sin omega t upon R. So, phase representation, the voltage and current in a resistive circuit are shown as, so both are in phase, only magnitude will change, diagram resist. The two phasors are exactly coincident, but are drawn slightly apart, so that their identity of each may be clearly recognized, because they have a different value of magnitude. So, now based on that, there are some of course unsolved problem which you can work out in the same manner, and these are the some of the references on which we have taken this today lecture, and thank you very much.